The next presentation, while I plug this in, is a bit of a bit of an outlier. So there's a group called the Open Source Radio Telescopes. I'm in frequent contact with them, but I'm not actually a core member. And I asked them to come to FOSDEM and talk about their work, because I think it's just really good stuff that they do, and like it just fits it perfectly into FOSDEM. But they couldn't get funding for like sending anyone out. So I said, okay, well, I'm not an expert on what you do, but if we can come up with a good presentation together, then I will just do it on your behalf, because I just want to get the word out there. Yeah, what's happening. So my name is on here because I'm giving the presentation, but Evan, Ellie, and Richard were the people who actually put this together, sort of as part of their initiative, marketing material, I don't know, whatever you want to call it. Okay, so that's that. Now, open source radio telescopes. What is this actually about? So it's a bit of a different group than the other people that we've seen here. So the idea is to provide designs and instructions for doing radio astronomy, with the intention of introducing them into sort of the education system, like making this become an easily accessible teaching tool. And now the idea is not necessarily to train hundreds and hundreds of thousands of people to become radio astronomers, but rather to get people interested in engineering and DSP and all those things in general. It just happens that the people who started this project, they're all astronomers, or some are professional, some are hobby astronomers, and they're all interested in sort of education. It is a good field to both build simple experiments that are still very, very impressive, but also to do some actual engineering work. So that's sort of the general idea. And the express intent is not to sort of reinvent the wheel, but rather use GNU Radio, for example, where possible. Just use cheap and easy things wherever available, and then focus on actually making it available to educators, for example. Okay, so this is some of the things that open source radio telescopes are currently doing. So there's this 21 centimeter horn antenna project. You can map out hydrogen lines that way, and actually draw a map of the galaxy. I'm going to show some pictures later on. A small loop antenna, which has a different application. So those are sort of two sort of practical things that sort of came out of this project as something you can do, and has instructions and all of that. So these are sort of projects, and this is sort of the process. So there'll be more and more instruction manuals and kits and all of those things made available. Yeah. And like I said earlier, so RTL SDR dongles, GNU Radio are sort of some of the main tools. Okay, let's take a look at those two projects that I just mentioned, and let's talk about them. And this one is what they call the small loop antenna. So you can see it there on the left. You can see this isn't. I mean, this is a pretty capable piece of hardware, but it doesn't look like it's very difficult to make, and it's not. That's the whole point. So if you take all the parts together, you end up with about $100. It's a bit of an estimate. It took a couple of iterations to sort of figure out an easy way how to do that. So yeah, the actual antenna is, I think I might actually have some more information here. The actual antenna is basically a long wire. There is a tuning part, so ham it up effectively, and amplifiers. So so you start up with just basically a frame, and so the geometry matters, but the exact carpentry does really not. So you wind a wire around it, and that's pretty much all you have to do. And then you need some electronics, and that's where the fun starts, I guess. So this is an amplifier and some filtering. and a ham it up is used to then, ham it up is then used to move the signal into a frequency range that is receivable by the RTL-SDR. So why do you need to ham it up? Because the idea is to track VLF signals. So VLF is used by the Navy for communicating with submarines. So you can think what you want about the world's armed forces, but they give us a lot of high-powered transmitters to play with, like with the passive radar. So VLF is it's pretty high power. I mean, so the point is that you have like this one big transmitter like somewhere, and you don't give away the location of your submarines because it's just basically available everywhere. It even penetrates water to a degree. And one thing it does is so VLF goes everywhere. And one thing that radio astronomers do, I don't know if they do it all the time, but in this experiment, it's a nice, neat effect. Is when there are solar flares, the ionosphere changes its charge level. I don't know if that's the correct physical term, which has the effect that VLF signals sort of bounce off the ionosphere earlier than they usually do. So, for those who've taken like ham exams, you are familiar with like these terms, but these are layers in the ionosphere. So for reference, if you do HF bouncing off the ionosphere, they usually do happen in this area, F1, F2. Derek, is that correct? And VLF bounces off a little earlier, and when you have solar flares, even more so. That means if you have a solar flare, the received power to your monitoring site is higher. So, and using that small loop antenna, you can measure that. So, and the kit includes all the software as well. So just quickly, so starting from the antenna, which is just the wire, the amplifying circuit, which you have to assemble, the ham it up, going in, putting it into an RTL-SDR, you end up now in software, GNU Radio for some pre-processing, and then there's another Python program that is sort of part of the OSRT kit that will then produce your graphs. And the graphs look, what? Where's my graph?
Total integrated power.
No, I think I just miss something. I think I was reordering the slides, and I think I did something wrong there. So actually, I'm just gonna stick to the order, improvise a little, and I apologize for misrepresenting the open source radio telescope project. So we'll see some results about that. The tools that were chosen, like I said, GNU Radio, RTL-SDR were evaluated. So SDR Sharp, for example, is another one that was evaluated. So I don't know if you've used it. It's one of those tools that you just like fire up, and then it immediately gives you nice GUIs, whereas GNU Radio is more on the like sort of reconfiguration side. But then, like I showed earlier, for the actual final project, then GNU Radio came into play. But this is an interesting thing because it it shows like the steps people have to go through for starting GNU Radio. And if you want to make a tool that is very easily accessible, and we're not even talking undergraduate students, we're talking like middle school students here, you have to make sure that you don't put in any pitfalls. So as someone who's representing the GNU Radio project, that's a good sign for us to make sure that we keep things simple. Okay, so the DSP is very simple. It's just FFTs basically. I don't really want to go into it because in the end we just plot everything into a waterfall. This is the flow graph, so nothing crazy in there. Like FFT is like the craziest, most DSP intensive block in the entire flow graph, and that's saying a lot. So yeah, and now finally we come to the results that I promised to you earlier. So this is just a very long recording using the small loop antenna. This is like 24 hours, so one full day, and I don't think you can read it at the back, but these are sort of annotations where the signal power went up, and it did coincide with solar flares. So I didn't know this either, but as you have like sunrise and sunset, like the reflection actually goes down, which are these dips here. So, But this is nice, and like you can. It's not like those just randomly happen, right? There's like forecasts for this kind of thing. So if you're like into the whole radio, ham radio scene, then you will know that. So that's a good time to set up an experiment like that. So more elaborate is the. How much time do I have, Marcus? I think.
20 minutes.
Oh, okay. Yeah, I've got plenty of time. I thought it was like 1 minute for a minute there. Sorry. Okay, the horn antenna is a more elaborate project. So it's also a little bigger. You can see, like, a laptop for scale here. This involves a little bit more carpentry. The sort of electronics part of it is it's a little bit more evolved at this point. So the basically what you have to do is you have to like. I have another picture showing from the front, but you have sort of a waveguide here, so you need to make sure that this gets appropriately captured. So you don't have to do the ham it up stage in this case, because I'll show you in a minute, will be for detecting the hydrogen lines, but you have to make sure that you have the signal properly amplified and matched and all those things. But in the end, you end back in the SDR dongle, go to GNU Radio, run a Python program over it, and take a look at the results. So in that respect, it's very similar. Okay, but why? Like, what's the difference? Like, why do this project, not the other one? So this is something you can use to measure the hydrogen lines. So this, if you look into the galaxy and there are areas with more hydrogen, like some nebulae or something like that, they will emit energy, and you can just figure out where they are by pointing the horn in different directions. Fortunately, the planet we're on turns around, so that gives you a good view. Also, this is just a more elaborate project. Can also mean more satisfaction for people. Maybe people do the small loop antenna first, and then they want to build something a little bit more interesting. And then this is a more just a slightly more elaborate project. Yeah, it's also a bit more expensive. So Evan, who's one of the authors, commented they're sort of trying to improve the kit to make it a little cheaper. So with $250, it's maybe slightly outside of the budget of some kid who just wants to buy the kit themselves, but it's still a very reasonable price. Plus, you get to keep the antenna. It's not like this is something you can't reuse or anything. So slightly more difficult, but also more interesting. So yeah, here are some pictures from the actual construction. So you have to sort of build a scaffolding frame, whatnot. This is, some boards and drywall. I'm not quite sure what it is. Obviously with reflective material, and so waveguide, low noise amplifier. Just put it all together, following the schematic I showed on the first slide. And there you go. So this is an FFT plot of the actual signal, and you can here, I don't know if you can see it, is a peak, just above the noise at 1.4 something gigahertz, and that's where the hydrogen line is. So this is pretty cool. You're basically looking at the galaxy at this point, and I can totally understand how that would fascinate people. Even if it's just this line, it's this is space and everything, and so really, really fantastic. Now, if you align this with some information about where you're looking, you get pictures like this. So, we don't have a measurement for every single spot on this graph, which is why you have these curves. But so I don't know how familiar you are with the galactic, coordinate system. I actually had to look it up myself, but basically, the galaxy is mostly flat, so you have one dimension, which is basically the angle between the sun and the center of the galaxy. So you'd expect, and the other one is going upwards from the galaxy. So you'd expect, as you increase the latitude, to see less stuff, because there's just no hydrogen there, and then that's exactly what we get here. So, and as you sort of sweep around, you can sort of correlate this with position of celestial objects that emit hydrogen lines. So yeah, personally I find this pretty cool result, and I can This is just very nice to be able to do like on a smaller scale things that radio astronomy labs are doing around the world. Okay, so that's the two projects. I'll talk a little bit about that's like the actual project that you can build. I want to talk about the project, the open source radio telescopes, just for a little bit. So they have a website and they have like instructions there and pictures, and you can follow this. And so they're actively like creating better instructions and manuals and kits, but they're also very responsive. And in particular, like people who ask questions where they show that they're interested but they have very little experience are very welcome on this mailing list. So like if you go on that mailing list and I want to do this, it's awesome, I have no idea what you like, promise you'll be well received and helped through all the way through to completion. So kudos to to the team for focusing primarily on like beginners at the very, very lowest level. And here's a couple of people that you can contact directly if you want to get involved in the project, but they're also all on the mailing list. Okay, so I say lessons learned, because now again, like these are not lessons I learned, these are lessons they learned, but I want to sort of I do want to bring this forward here because I just love people getting involved in the educational sector. So these projects might look simple, at first glance, but it is a lot of work to come up with a sort of a kit and a whole project and a description of how to build something, from scratch. So, but I'm glad they took that all the way to completion, and now we have this to to spread the word, and it's something we can use as projects ourselves if we are in the teaching sector. And there's a lot of radio astronomy things you can do without like having access to the Arecibo dish or something like that. So if maybe you're already interested in astronomy, I mean like not radio but your regular astronomy or telescopes, and this is sort of a very nice extension to that. And plus you sort of trick people into learning all these engineering concepts, which is the whole point of this exercise. Okay, there's a couple of people who were all involved in building these things. I might actually put it up again. I do have a couple more pictures here. So this is Ellie, who I worked with on this presentation. You can see here Eve Klopp from Oregon Institute of Technology, I think so, with her students, building one of those dishes, and they seem very happy. So, okay, I'm gonna go back to this guy, and I'm gonna, ask you guys to give them a round of applause for putting this all together. So. So we have some time for questions, and I will actually try and answer them as best. And Derek, thankfully, who knows a lot more about actual radio astronomy than I do, has agreed to help me with any questions. So yeah.
Actually, I'm very glad that you answered this, because the first thing I did when I was reading the FOSDEM program was to read them and discuss about last year's presentation about ion stream testing.
Oh, cool.
Then my question is, what is the rationale of using the RTL dongle receiving 24 kilohertz as opposed to the sound card, which meets Nyquist criterion but gives you 16 more bits on the detection? So why upconvert the 24 kilohertz as opposed to using even the 48 kilohertz sound card will do the trick?
So you mean for the VLF signal, right? Yeah, that's a good question. I mean, so I can say this is a bit of for one, it'll make the whole thing simpler, because like it's the same solution for one way or the other. Plus the RTL-SDR doesn't actually drive the price a lot. I think the ham it up might, I'm not quite sure how expensive they are.
$30.
Yeah. So I mean, it does add some cost. Like I don't know about matching and everything. Like how do you get the antenna signal into your sound card like well enough? Do you know? Do they?
An amplifier.
Yeah, well, yeah. You'd need a different amplification circuit. That's for sure. I think it's just much easier to match I'm just completely like guessing here, but it's probably easier to match your antenna to an RTL-SDR than it is.
In both cases, your antenna has a huge impedance.
Yeah, you're right. Yeah, it's.
So actually the operation amplifier, you're not so much looking at amplification than impedance matching. You have your 1 megabit input, and you will feed sound card of RTL.
Yeah, we have this op-amp will drive line in for easy.
Yeah. See, that's what I get for making stuff up on the spot. Yeah.
I think another part of the consideration was that it was an interchangeable component
Yeah, exactly.
with the hydrogen 1 antenna.
Yeah, that makes
Um,
sense.
and also its general purpose at that point, so you can show spectrum at other areas, and it's an extensible tool at that point.
So if you have a student coming out of this saying, "Oh, this is awesome. What else can I do?" It's like, "Oh, you can also run like some other software, and boom, you do AIS or whatnot." So I think that's like the main advantage. Okay, and I'm glad you you got in touch with those guys. Any other questions?
Just a remark, I did similar activities, but just hunting for a signal in a building. Just give them an SDR dongle and you hide somewhere a signal and they will discover about what's happening in the RF.
So like a scavenger hunt.
Yeah, you can, like that. It's quite easy to do.
Do you have like? Did you like talk? Do you have like a blog post or something like you can?
Of course, about this, but not that complicated. So it's really the idea could be nice for this.
So like cool experiments don't have to be complicated. I don't know how many people we've shown like FM demodulators with GNU Radio, and it's like, you know, every like $20 radio has better FM reception than GNU Radio does if I don't like tweak the software. But it's just like the you know, it's just way more tangible and people get excited about it. So I can, from my own personal experience, I can say like have people do simple experiments with SDR, and you know, many more people will enjoy it than you might expect. I think you had a question? No? Okay. Any others?
So I'm not an expert in this, but are they planning to do something into the direction of synthetic aperture applications? Because like they want to take four antennas, right?
Right.
You have the RF, and it should be very nice to be some of the radio.
So I don't know that they're doing that project. Yeah, I'm trying to speak into the microphone a little bit for the recording. I don't know that they've done that,
Actually,
but
can you
there's
repeat the
certainly
question?
the question is, are they considering doing a synthetic aperture or multi-antenna setup? And I don't know that they are. I kind of doubt it, simply because the RTL SDR needs a lot of work before you can do that effectively, and the hardware that can do it effectively is more expensive. But there are certainly many other people, myself included, who have done things like that. Marcus Leach is an excellent resource if you look him up. And the general term is interferometry when you tend to speak about it with radio astronomy. And you can very effectively create a 4-antenna interferometry receiver and get very good results with all the kind of classic benefits that you get of improved narrower beam width and physical resolution. And it's certainly something that you see with like the square kilometer array and many of the professional radio astronomy setups. So there are existing tools in GNU Radio and outside to do it. And there's an entire radio astronomy GNU Radio out of tree module to handle that. And it's targeted interferometry.
And just to like give a final thought, like without having spoken to these guys, like a synthetic aperture radar and interferometry, I would probably like rate more like an undergraduate project, whereas they're really aiming at like getting the bar down low. I mean, so we have time for like 1 or 2 more questions. Okay, well then, yeah.
I'll throw out one comment. If you are looking for something to look in the sky, pulsars are a very easy target, 408 megahertz. And one of the interesting things about them is because there are so many, most are not observed all the time. And so some very notable astronomy conferences include works from just random people who have stared at a pulsar for a year and said, look at the data. And so that is a very interesting topic that can be done with like a tape measure Yagi and a very basic SDR.
Okay. Well, thanks to these guys. Yep.